Hello, I'm Will. Welcome to ResearchPod. For most people, on most days, a weather forecast is a convenient answer to, do I need an umbrella? How windy will it be? Simple questions with simple answers that you can usually trust. For high-stakes questions around landslide hazards, how do we deal with slope failure forecast? And are there any new tools improving our capabilities without waiting to learn from another disaster? Andrea Manconi, research scientist at the WSL Institute for Snow and Avalanche Research, SLF, joins us to discuss new satellite data and methods to get ahead of the next slope collapse. Andrea Manconi, hello there.
Hello.
For myself and for everybody listening at home, could you tell me a bit about you, your work, where it is you're located, and what kind of areas your research covers?
Yeah, I'm originally from Italy and specifically from Sardinia. So I did my master in engineering there. And after that, I've been working as a PhD student in Germany, specifically in Potsdam, where there is a big research institute about geoscience. And after that, I've been working back in Italy in a research center. It's called the National Research Council for about 7 years. And since 8 years now, I'm in Switzerland working in the framework of the ETH domain. So 6 years first at the ETH Zurich in the university, basically, working as a lecturer and researcher. And since 3 years now, I'm working in the WSL. So this is the Federal Institute for Forestry and Snow and Avalanche Research. And I'm based at the moment in Davos, high up in the mountains at 1,500 meters, where we work mostly on alpine research in different aspects.
Mm-hmm. And to think about, just the geography of your research has reflected a very alpine region. Would you say that the geography that you've grown up in, the influence of nature, has led your research development, or have you gone to those places seeking out mountains, slopes, and that kind of environment to work in it?
Yeah, it's a kind of interesting path. So I've been always attracted by natural environments and also to understanding a little bit how the processes are dominating a little bit of what we experience daily on the climate, and also, let's say, the natural phenomenal natural hazards like earthquakes or volcanic deformation and volcanic eruptions. And actually, my PhD was more in that direction. So geophysical hazards like earthquakes and volcanic activity. And then I just specialized in natural hazards that are related to mountains, but I was not seeking for that. So there are many colleagues that they are passionate about mountains, that they are always trying to work in this kind of environments. For me, it was, I wouldn't say by chance, it's still a phenomenon that is really interesting to me, but I was not searching for it. So now I'm focusing on this kind of processes. But from time to time, I still work also with former colleagues working on earthquakes and volcanic activity. So my interest is quite broad in this sense.
And what is it that makes your research timely? What is it that makes the paper that we're discussing something that is worth bringing attention to now? Kind of what is the running clock on it?
Yeah, so I think it's quite clear that climate change is now attracting quite a lot of research because we are experiencing in the last years a kind of dramatic change that I think in the everyday life, everybody is somehow experiencing with these extreme events that are usually affecting very delicate areas of our planet, and mountains are actually one of the delicate areas, and they are called the sentinels of major changes that we can experience in the future years. So in the high elevations, we have quite the critical conditions that changing, for example, the temperature, or having extreme events in terms of precipitation or in terms of less precipitation of snow, for example, would modify completely the environment and also the perception that we have in this environment. So I think the research we are doing in the alpine areas, so generally speaking, we talk about Alps, usually referring to the European Alps, but this term can be also used to define the high mountain areas. So this is usually in research also used just to describe the environment that is above the tree line, let's say. So this is where glaciers or rock glaciers or this kind of phenomena occur.
the inciting incident behind the paper that brought your attention to us and our attention to you was centered out of the Marmalade. Is that Marmalade? Marmalade?
Yeah, no, it's Marmal. You're pronouncing correctly.
Okay.
And so it's a glacier. This is quite a famous glacier in northern Italy, in the Alps. And in 2022, there was a big event that also attracted a lot of media, and mainly because there were some victims. Usually, this is also what happened. We have major events, let's say major failures that are occurring as natural events in many mountain belts across the world. But of course, this comes to the news only when there are some victims or some damages that are affecting infrastructures, for example. And then this topic is brought to the media. And in 2022, there was this event. It was a failure of the glacier in summer period where this area is basically visited by a lot of tourists, hikers that are climbing up towards the top of this mountain. And a portion of the glacier collapsed and basically was killing some people. So during that event, of course, I've been, let's say, working in different scenarios where this happened. But that time, it was kind of mixed between the emotion. So because it was an event occurring in Italy, and of course, this touched me. But also, I was trying to think what our scientists in this domain, and including myself, are bringing to trying to avoid this kind of scenarios. So many times in scientific conferences, when we present our results to our peers, we try really to deliver so our advances in a form that could be helpful for the people. But I really felt that we had to provide something soon, now, and not just think at the longer perspective, because this kind of events, according to what we expect from the climatic modeling, might increase over time. So we need to have proper strategies to deliver solutions that might be really applied for this kind of scenarios.
Well, you mentioned about doing something soon, and I'd like to follow the idea of time because, mountains feel like they are eternal or forever to the bystander. Like snow is seasonal every winter. But if we can think about how fast the circumstances on a mountain or on a slope can change, and how quick predictions or reactions can be to see that, that instant shift of, snow builds up for months and months and months, and then in a second, an avalanche happens. What's kind of the clock again there?
Yeah, this is true. So it's really one of the interesting points that we are trying to understand. So we know that there are some processes that are developing over hundreds or even thousands of years, and suddenly, or changes that might be really little, then we experience a failure or a dramatic evolution or a very rapid evolution that maybe is not coming to a failure. So, and this is actually the part of the research we are trying to develop, understanding the physical processes that are dominating this slow evolution towards a potential catastrophic evolution. It is true that glaciers been always moving, so we know that they are basically displacing all the time in summer because of the temperature. We know that some crevasses they fail from time to time, but according to the climatologists and on the expectations of the future years, this increase in temperature might also increase the instability in the high mountains and might also increase the probability of occurrence of phenomena of this kind, like the Marmolada Glacier or all the events that have been also experienced in the Himalayas and in other mountain chains.
And a lot of your work in this paper is centered around prediction rather than reaction, because, it makes sense that if you can prevent catastrophic loss of life or, be there soon enough to rescue people, then that's better than too late. So, to think about running that clock backwards into predictive territory, how does the field at the moment predict slope failure? If we can break things down into a simple language, simple chunks of information, and then build up to what your research is putting forward as the next necessary steps.
Yeah, we basically look at the mountains like a doctor would look at the human body, let's say. So we try to monitor some parameters. And so, for example, to monitor parameters of the human body would be temperature or would be the blood pressure or all the parameters that you could basically analyze to have some quantitative information, so numbers that would be helpful. And also in mountains and the slopes, what we can do is to measure these kind of parameters over time and understand whether there might be some changes. One of the parameters that we are used to control with monitoring systems is the displacement or the deformation that is occurring at the slope. This is something that is happening at the surface and is relatively easy to measure with different kind of instruments. So, and the idea is really to monitor the evolution of the displacements over time to identify if there is an acceleration or if there is a change in the pattern that we would expect for specific seasons. And in case there is an acceleration, then react and try to model what is the evolution in the future. So just, I don't know if I can bring some relatively easy mathematical concept. So what we've been working on since the 80s is a very simple model that is called the inverse velocity model. So you basically calculate the inverse of the velocity of the measurements that you have of the surface deformation. And probably everybody reminds, so in math lectures, that if you calculate the inverse of a number that is a really high, really large number, you basically go towards zero. It will be smaller and smaller. So the inverse velocity modeling exploits this concept to calculate when we would reach the zero. So meaning that if we have an increase of the velocities over time, we would approach the zero in a certain time window, and we can try to predict when we would reach the zero.
It's interesting to think of, being able to pin a countdown clock to something. Is it as easy as, putting a little stick in the snow and waiting until the timer hits zero? What's the necessary technology here?
Yeah, so there are several techniques. So the displacement can be measured with different techniques. So there are some techniques that are putting just points that can be measured over time through, for example, cameras. So standard photo cameras, this would be one possibility, and then measure the change of position over time. Can be with a GPS technology, also having points that are also changing their position over time. Another rather common instrument is what is called a theodolite or a robotic total station. You probably have seen several times along the roads some technicians that are making measurements with some strange prisms, targets, and they are basically measuring the distance between a sensor and the target and basically having the location of this target. We can use the same principle also to track the evolution of points over time. They are very precise. You can go up to millimeters of deformation. And this is something that is really attractive. But the problem is that up in the mountains, sometimes it's not so logistically feasible to install instruments. So that's the reason why in the last years, remote sensing technology picked up. So I was making the example of cameras. But cameras, they have the disadvantage that they are in the optical domain. So when it's dark during night, you cannot use them. When there is a bad atmospheric condition, you cannot use them. And this would be the same if you have a camera installed on the ground at a certain distance from your monitor target, or if you have a camera or a sensor of the same kind in a satellite. So we would have the same problem. We can just monitor over the daylight and also when we have good atmospheric conditions. So that's the reason why, since almost 30 years, a new technology has been developed in the domain of radar. So there's basically microwaves that can go through the atmosphere and reach the targets. And this is very convenient because you don't need the source of light to record the information. So it's an active microwave sensor that is sending waves to the ground and then recording the delay that these waves have while traveling across also the atmosphere, touching the target and getting back to the sensor. And with this principle, with radars, we can measure the displacement of several points. In this case, we are talking about the mountains or a slope that is moving or a glacier that is moving. This is basically what we are using more and more in these years.
I'm going to keep coming back to the theme of time here because I know that if I look at the road that I live on Google Maps, it's not there. The map hasn't updated yet, and buildings have been here for several years. How quickly are the satellite radar scans that you are working with updating? How contemporary is your information?
So this is exactly the point. So we might have a very good spatial resolution, so the possibility really to map and image some features with a very high accuracy in space. But what is really critical, especially for the topic we were discussing before about prediction, is the timing. So meaning that we need some sensors that are passing as often as possible to catch changes. And this is exactly what I developed after the event of the Marmolada. So I wanted to use satellite data, specifically in the radar domain, that could bring us information possibly on a daily basis. So most of the satellites of this kind with radar, they provide you information every several days. So they are ranging between 40 days, so like in the range of months, or up to 6 or 10 days, 1 week, 4 days. But for rapid evolutions like what we have seen in events like the Marmolada, we need really to have updates at least daily. This would be really an important achievement to try to predict what is happening over the next days.
And is there somewhere that something like even civilian, domestic drone technology is stepping up to fill that gap?
Yeah, so there are some experiments that are also based on drones and civilian techniques. Of course, in the military domain, this technology is being used and is quite reliable already for these applications. But in the civilian domain, we have since few years also commercial satellites that are providing these data sets timely. So this is because the technology advanced a lot in the last years. The cost also for shipping satellites is much lower compared to the past. So meaning that we are now experiencing what is called the golden age of remote sensing and specifically of radar satellites, because we are starting having not just one satellite, but a constellation of satellites. And this is allowing, so the constellation is increasing the probability that one of these satellites is acquiring information over our target globally. So that's the main difference compared to the past.
Now, there is some part of me that wants to weigh those advantages against. There's got to be some disadvantage, like if I don't know, the amount of emissions for any rocket launch then contribute more to global warming, or if you're doing daily flyovers with a helicopter, then that comes with emissions as well. Is there any trade off in terms of downsides, or is it all just better and better as a golden age?
Yeah, it's always one of these issues. You have to balance a little bit what is the advantage that you are bringing with this new technology and what would be the disadvantage. I never thought about doing a balance, so like a CO2 balance of what would be the benefit of my research activity or for the acquisition of launching multiple satellites. But for sure, we are also attentive to this kind of problems now. And remote sensing based on satellites is probably from this point of view, less costly compared to helicopter flights or just fly with drones as well, just because you can cover much bigger areas with a single acquisition. So you can cover several kilometers or you can cover globally, while if you would have to do the same with helicopter flights, it would be just a completely different amount of emissions that you would have to count.
Well, there was a case study in your paper of putting some of these advances, some of these practicalities in the field. Brinzals, am I getting the pronunciation there correct?
Yeah, Brienz is basically is a slope that is located close by to Davos, where we are based, and we are working since several years in this area. It's also an interesting case scenario because there is a village on top of the slope. So this is quite well known that there is a landslide going on there since many, many years. And also in, I think, 1864, there was already an evacuation of the village because of an acceleration of parts of this slope. And recently, we experienced also this kind of acceleration again of a portion of this slope. And that was basically the connection between my thoughts after the Marmolada glacier collapse, where we basically arrived after the collapse. While here in Brienz, we experienced this acceleration and we could test some of these techniques that I mentioned with the radar and with the possibly a daily coverage with this technology in an area that had also a similar hazard potential. So we acquired a lot of this imagery with radar over Brienz. And in June last year, so in 23, there was finally a collapse of a portion of this slope. So what we basically have done is to process the data in a timely fashion. So that's showing that it's really possible to process the data almost in near real time and provide information that would compare well with ground-based sensors. So one of the issues with these new technologies is always that you have to validate their performance to be comparable with all the technologies that are there since many, many years, and they are reliable. We did this experiment and it was successful. So the prediction capability that we had was similar to what you could achieve with ground-based monitoring. This means that in cases like Brilliance, where we have a full control of what is happening, we can validate this technique. And now we can try to approach with the same methodology also all the slopes where we don't have a full control, like here in Brienz, or all the slopes in Switzerland or in Europe in general, where we can reach relatively easily the slopes and we can also install additional sensors. But you can imagine in places like in the Himalayas, where the size of this phenomenon can be much bigger, and also the vulnerability of the populations and of the infrastructure is a completely different level. If we can afford doing predictions by using remote sensing data instead of going there, which is logistically quite complicated and also very expensive, then we have the chance also to use this for predicting the evolution and maybe just trying to avoid this kind of disasters occur, or at least mitigate the impact on the population. Because in some cases, there's nothing you can do. You can just warn people, warn the authorities. But I mean, in the end, what we are really keen on is saving life, if possible. Then, of course, infrastructures, you cannot move them if they are in a location that might be affected by a failure.
Well, is there anything that you see in maybe future developments or, I mean, the big trend at the moment is to say, what can AI do for this in terms of data analysis, monitoring, and kind of the processing of the huge amounts of information going in and stratifying information going out? How do you think this could improve either response times or predictive power in those ideal situations in Europe in the Alps, like you say, compared to places like the Himalayas?
I mean, one of the issues is, of course, that by having an increasing amount of data, we need to have some models or strategies to process this data and to really interpret this data in a timely fashion. And this is something that we are working on. So we have several projects that are also trying to develop methods in the AI domain to help us in the mapping and interpretation of this kind of phenomena. On the other hand, I think this is usually also what I say to my students when we have lectures in this domain. One of the problems we have in remote sensing and in natural hazards in general is that we don't have sometimes enough data to train models and to train the machines to provide us the right answer. So meaning that we still have to learn a lot before teaching the machine how to help us in the future. So at the moment, we are still acquiring a lot of data, and this would be for sure in the next year beneficial for the AI development in our domain science. But we are not yet at the point that we can really develop an AI model that could be really helpful for the interpretation and maybe the prediction on where, how big, and when a new failure will occur.
To keep coming back to the theme of time, we've talked about the past of developments and the present of your research and the future of where this might go. And we are now coming to the end of our time with you here today. So, for anyone listening to this who is maybe interested in your research or in climate change and in glacial shift, what would you say would be the key takeaway for a member of the public, let's say someone who is living on the slopes in Switzerland or in Italy and is worried about their future, or a different takeaway perhaps for a politician, someone who would be in place to direct people in that disaster response?
Yeah, this is a very important point because in many cases, the products that we have are scientific papers that are delivered in the scientific community. And so there is a little distance between what we deliver in the scientific community and what actually the people are really taking as a message So we are now also trying, and I think this podcast today is also part of this process. We're trying to deliver this information also in a way that the people that are not involved in the scientific process, they could also pick up these concepts. And we have some papers or some products that might be more accessible also to people without having the scientific background. And usually, I'm talking now about the Swiss level. So there are the cantons and the federal government that they are producing also some information that is really useful in terms of guidelines. So I think this is really now also part of the job that scientists have to do in cooperation with politicians and also other actors, try to deliver this information in an easier way and also to avoid an excess of panic. This is also something that is really important. So we are working on trying to better understanding what is happening in the high mountains. We are not yet at the point that we can provide an interpretation that is final. We are not capable of predicting what, where, and how big, as I said before, and when something will occur. But we are trying to go in the direction of like the meteorological predictions. So, I mean, everyone accepts that sometimes these predictions might be not accurate enough. So having more data, having more information will help us to go towards this potential prediction of large failures also in the mountains.
And on a personal level for you, where can people find more from you, either on social media or on a university page to follow your work?
So there is a website of the WSL, which is www.wsl.ch. And in this webpage, you can find a lot of information in different languages about several projects we have in the research domain and also applied projects. So there is a specific web page also for all the research groups. So the people can find out also specific information about the projects I'm working on. And so I'm personally delivering most of my social media in LinkedIn, not in any other platform. So that's basically where people can find some more information, more updated information on my research.
Thank you so much for your time, Dr. Manconi, and all the best with hopefully getting ahead of those predictors and forecasts soon.
Thank you very much.